Welcome to this lecture. This is the final lecture of week 6. So before proceeding with the discussion of this lecture, let us first quickly recall what we have been discussing in this week. So in this week we have looked at the integration of measurable functions with respect to the given measure on the domain side. We have also seen some major properties of such integration, and in particular in the last lecture we have finally discussed about the linear structure of such an integration. In this lecture we are going to use all these properties and restrict our attention to the special class of random variables, which is the class of discrete random variables, and compute their expectations. So we are going to see that the expressions that come out while computing these expectations of discrete random variables will be the same as considered in the case when we discussed it in the basic probability courses. So let us move on to the slides and discuss things in more concrete detail. Alright, so let's start with this idea that expectation of a random variable as defined in this course is through that measure theoretic integration. Now we restrict our attention to these discrete random variables and we would like to simplify that definition to a more manageable level, and we would like to see how it comes out. Alright, and we would like to say that it will at the end reduce to the familiar series expression for discrete random variables. So before going to the explicit computations, we require few more results. So the first result in this direction is called the change of variables or change of measure. So you start off with one measure space omega 1 script f1 mu1, so that will be taken on the domain side, and then take a measurable space on the range side, and what you do is that you look at a measurable function, call it f, from the first measurable space to the second measurable space. Now you are going to construct a set function, call it mu2 f script f2, which is on the range side. So this should be a set function taking values between 0 and infinity, infinity included. So we define it through the pre-images of all arbitrary sets on the range side under the function f. So you look at these pre-images, and this set is now on the domain side, sigma field script f1 by the measurable structure of the function f, and you can consider the measure with respect to the mu1. Okay, so what is this measure? That value gets associated to this set function. Alright, so we first claim that this set function thus defined is a measure. Further, we want to claim that for any measurable function now on the range side, defined on the range side, taking values in the real line, call them g, we have this integral relation. So you are changing measures from mu1 to mu2, where you are considering the integrations over mu2 for sets coming from the range side, and when you are considering integration with respect to mu1, you are of course considering sets on the domain side. But here note that corresponding to the integration over a set capital A on the range side, you are going to look at the integration of the pre-image of that set. So that's where the integration will be concentrated on when you are considering the domain side of it. Okay, so this is the relation that will allow you to do change of measures from mu1 to mu2 or mu2 back to mu1. Okay, alright, this relation will hold when at least one of the integrals will exist. Okay, alright, so before proving this, let's first see what this result suggests. So take the set capital A to be the whole set on the range side. Then what does it say? It says that you have this relation between integration of g composition with f on omega 1 and integration of g on omega 2. Okay, so here we are using the fact that since f is a function with range which is possibly a subset of omega 2, so the pre-image of whole of omega 2 is nothing but the whole domain. So that's what is being used here. So that's all will allow you to write down this equality. Okay, now let's focus our attention to the case of random variables. For random variables, on the domain side we are given a probability space, and on the range side we are given this familiar measurable space which is the real line together with the Budel sigma field. Now consider the previous case, the general case as given in that theorem. So what you do is that you take the domain side measure space to be omega fp, the probability space, and the range side measurable space to be the real line together with the Budel sigma field, and take the function measurable function f to be the random variable x. Then you enter the familiar picture that the measure mu2 that you have thus defined is nothing but p compose x inverse, which is the law of x. So we have extensively discussed about the measure theoretic properties of this p compose x inverse, and the fact that p compose x inverse is a measure, that also has been discussed earlier. So following the similar argument, you can now try to prove that this mu1 compose f inverse, now this is a more general structure as stated in theorem 3 above. So this is a more general structure, but it follows the same proof, same argument that will allow you to show that mu2 will become a measure. Okay, so for the case of random variables, you actually had that p compose x inverse is a probability measure, but in general for general measures mu1 and general measurable functions f, you will only end up with a measure. So the push forward of a measure by a measurable function remains a measure. So this argument is left as exercise, but as mentioned earlier, this discussion simply is the same as done for the case of p compose x inverse, the law of a random variable x. Alright, now continue with this situation. Okay, now choose this g function from real line to real line itself and assume that it's Budel measurable. So choose this function g to be x itself, the identity function. Then by theorem 3, what you can now say that for the whole range side, take the set capital A to be the whole range side. Then what is the pre-image? Pre-image is the whole domain, and therefore you have this change of measure relation that x integration of x with respect to the probability measure p that we have been considering while talking about the expectation of x can now be written as an integration over the real line by changing the measure from p to p compose x inverse. So that's all is the application of theorem 3 when you are talking about random variable. So you are changing that integration from over omega to the over real line, and you have this integration now that will come from the choice of the function g as the identity function, which takes a real number x to itself. Okay, so therefore you have now rewritten the expected value of x as integration over the real line with respect to the law p compose x inverse, where p compose x inverse is a genuine probability measure on the real line. Alright, so therefore your original definition that was via this probability measure p on the domain side now gets transferred to the range side in terms of the law p compose x inverse, and this relation will hold provided one of the integrals exists. Okay, so this is as per the theorem 3 above. Now this is allowing us to write this expected value of x in terms of the law p compose x inverse. Okay, so this is therefore saying that fact that expectation value is purely dependent on the law p compose x inverse. So you don't have to worry about the actual probability measure p or the actual random variable x. As long as you know the law p compose x inverse, just look at the integration over the real line given by this. Okay, and if you can compute this, you can get the expectation value of x. Alright, so again continue with this, but let's now choose a more general function g here. So instead of the function gx equals to x, now choose a more general function. So what do you do here? Now here what will happen is that you can now consider expected value of the random variable g composed with x or g of x, and that as per definition is the integration of g composed with x of omega here with respect to the probability measure p. But again, if you change variables, you again end up with this integration which is over the real line now. So you are trying to integrate this measurable function g on the real line with respect to the probability measure p composed x inverse. So again, if you can make sense of one of the integrations, then this equality holds, and moreover, if you can compute the integration over the real line as given here, you don't have to compute the integration with respect to the probability measure p. You can just take that same value and consider it as the expected value of g of x. Okay, so this is the advantage, that you are transferring all the information in terms of p compose x inverse. Alright, now here is a interesting observation. Choose the function g of x equals to mod of x. What will happen here is that then you are getting the fact that expected value of mod of g of x or expected value of mod of x, that is exactly equal to integration of mod of x with respect to the measure p compose x inverse, right? So instead of checking this complicated integration of mod x with respect to the probability measure p, you may alternatively check this condition, integration of mod of small x with respect to the probability measure p compose x inverse over the real line. So instead of doing the integration over the domain side omega, you do the integration over the range side which is on the real line. Okay, so this is the alternative condition and may be easier to work out. Great. So with these observations at hand, let's now go to the proof of theorem 3. Alright, so again we take our familiar approach. Here omega 1, script f1, mu 1, these are fixed, the function f is fixed, and what you want to do is to show that for any measurable function g will have this relation, appropriate relation. So that is what we want to show. First comment is that g composition f, that will be measurable because composition preserves measurability. So as long as the composition is defined, you will get a measurable function. So g composition f here is defined on the domain omega 1 with the sigma field script f1 and the range as the real line together with the Bodel sigma field. Alright, now what do you want to show is that you want to show that appropriate change of variable formula or change of measure formula holds. To do that, we follow our familiar approach. We want to prove it for indicator functions first, and then we would like to take it over by linearity to simple functions, by limiting arguments to non-negative measurable functions, and then finally by linearity to general measurable functions. So let's verify the equality when g is an indicator. Choose a set B on the domain side for g. Here what is happening is that you want to verify this integration equals something else with respect to the integration with respect to mu 2. Alright, so let's start with this expression and put the fact that g is nothing but this indicator of b. So when we put that in, put in the definition, so this is f of omega 1, we are checking whether it's in the set B or not. Alright, but then that can be rewritten in terms of f inverse of b, and you can just check whether the point, sample point small omega 1 belongs to the set f inverse of b. So observe that f of omega 1 belongs to the set B if and only if small omega 1 belongs to the pre-image of b under the function f. So that's all we are using here. But then the integration is over the set f inverse of a. So if you put in the definition for integrations like that, then all you have to do is to look at the integration over the whole set and multiply by the appropriate indicator of that set. So earlier the integration was over f inverse of a, you just brought in this indicator of f inverse of a and you could now do the integration over the whole set omega 1. Now this is the product of two indicators, so therefore as observed earlier, this is nothing but the indicator of the intersection of the two sets. So just write that down. But then you are now saying that you are going to integrate the indicator of some set with respect to the measure mu1, right? Now using the properties of the pre-image, you can also rewrite it as f inverse of a intersection b. Now, since you are just doing the integration of this indicator function, then this is nothing but mu1 of the pre-image of A intersection B. So that's all you are doing here. Great. But that, as per definition, mu2 is nothing but mu1 compose F inverse, and therefore that's all you write, that this is mu2 of A intersection B. But then you can easily write it as indicator of B d mu2 over the set A. So this is the integration of this indicator function with respect to the measure mu2 over the set A. Alright, so that's just rewriting this integration procedure. Great. So therefore you have now proved the required equality when G is an indicator. Okay, now follow the standard approach. Use linearity and limiting behavior to extend it to any general measurable function, provided the integrations make sense. Alright, great. So that completes the proof for theorem 3, and this allows us to state this result, that change of variable or change of measure is possible when you are talking about this measure theoretic integration. And in particular, we have already commented earlier that one of the useful implications of this theorem is the rewriting of the expression for expectation of x, which can be written as now integration over the real line with respect to the law P compose X inverse. Alright, so now before doing these explicit computations, we need couple of more results, and which are stated below. Alright, so this will help us to do the simplification in our arguments. Alright, so let's start with any measurable function defined on the real line. Alright, so here we are talking about real valued measurable functions defined on the real line. So what do you want to do? We want to first look at the integration of any such measurable function f with respect to a Dirac measure. So choose a point A in the real line and look at the Dirac measure supported at the point A. Then we claim that the integration of this measurable function with respect to the Dirac measure is nothing but the evaluation of the function at the point A. Okay, so this is a very simple relation. This says that once you try to integrate a function with respect to the Dirac measure, all you have to do is to evaluate the function at that point. Alright, so how do you verify this? Again, follow the standard approach. First verify it for the case when f is an indicator. So let's see this. So if f is an indicator of B for some Borel set B, then put in the definition. So indicator of B evaluated at the point X. Alright, but now this is nothing but the Dirac measure applied to the set B. This is as per definition. So if you integrate an indicator function, all you have to do is to look at the size of the set with respect to the given measure. So that's all you are doing. But observe that Dirac measure associates these values, that if the point A is in the set B, then you associate the value 1, otherwise you associate the value 0. But you can rewrite this in terms of the indicator in this way, that this is the evaluation of the indicator function at the point A. Right? This is just rewriting the relation or the values of Dirac measure in terms of an indicator now. Great. But now what was indicator B? So that was your choice for f in this simple case. So you have verified the equality when f is an indicator. But then what do you do for the general case? You apply the appropriate linearity and limiting arguments to go to the general case. Okay, so as soon as you verify it for indicator functions, and then standard procedure takes over, as long as all the integration makes sense, the equalities will continue to hold. Alright, so this is one of the main results that will help us in computation of expectations for discrete random variables. But then there is one more result that we need to recall from our earlier discussions in week 2. So recall from this exercise 5 that addition of measures gives other measures. Okay, so what was this? That if you have a sequence of measures, let's say, then what you will get is that mu1 plus mu2 plus mu3 plus dot 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 will give you a measure. You can also state the same result for finite such number of measures. So if you have mu1 up to mu(n) are measures, then mu1 plus mu2 up to mu(n), that finite sum will also be a measure. Alright, but then there was also this another operation which was scalar multiplication, right? So if you choose positive scalars and multiply it to a measure, then you get other measures. So in fact we had used such operations to scale finite measures to probability measures. But of course, given any general measure, you can multiply by a positive scalar and get other examples of measures. Great. So with that result in mind, we now look at the integration of measurable functions with the measures thus constructed. So in particular, let's take two measures, mu1 and mu2, and we claim that integration of this measurable function over this measurable space omega f, where we are assuming that all the measures are defined. So if you are going to integrate the function f with respect to the measure mu1 plus mu2, all you have to do is to separately integrate the function with respect to mu1 and with respect to mu2 and then add them up. And the same relation is true when you are talking about this infinite combination of mu-n's. So all you have to do is to individually integrate them and then add up the results. And finally, for scalar multiplications, if you multiply this measure by this positive scalar alpha, then this alpha can simply come out of the integration, and all you have to do is to integrate the function with respect to the given measure mu. So these results will continue to hold provided the integrations that you are looking at or the terms that you are looking at on the right hand side make sense. In particular, if you are looking at these infinite linear combinations, you cannot have infinity minus infinity situations anywhere. So again, as long as these summations make sense, you can get these equalities. Alright, expressions on the right hand side hold. As long as they exist, you can talk about the appropriate equalities. So this is one other result that is going to help us in computing the expectation for discrete random variables. Alright, so how do you prove this? So let's go back to the statements 1, 2 and 3. So the statement 2 is just a generalization of finite addition to infinite additions. So once you prove it for the finite additions case, the argument will follow by some appropriate limiting procedure. So that will be left as an exercise. So let's first focus our attention to Roman 1 and Roman 3. So in Roman 1 we are talking about finite additions, finite number of additions, and in Roman 3 we are talking about scalar multiplication. So let's try to work them out, and again we are going to use this familiar procedure that we are going to work with indicator functions. Alright, so let's choose this function f to be an indicator of some set b, where b is coming from the domain side. Okay, so let's look at the integration now. So f is chosen to be indicator of b, and you want to integrate it with respect to the measure mu1 plus mu2, but that is nothing but the measure of the set b with respect to the measure mu1 plus mu2. Now as per definition, this is measure of the set b with respect to mu1, and you are going to add to it the measure of the set b with respect to the measure mu2. So that is as per definition of the set function mu1 plus mu2. But then individually they are nothing but integrations of the indicator of b with respect to mu1 and integration of indicator b with respect to the measure mu2, and therefore you get the required relation when f is an indicator function. Alright, let's try to verify same relevant equalities when f is an indicator and the measure is getting multiplied by a positive scalar. So let's try to look at this. So let's again put in that f as indicator of b, and then again put in the definition. So this is the measure of the set b with respect to the measure alpha times mu. But again, as per definition of the set function alpha times mu, this is nothing but alpha times the measure of the set b with respect to the measure mu. But then you write mu of b as the integration of indicator b with respect to the measure mu, and that's nothing but alpha times the integration of f with respect to the measure mu. So therefore you have verified the required relations when f is an indicator, and the general case will follow by the standard arguments. All you have to check is that the necessary integrals exist. If the integrals exist, you can ensure that the equality holds by this standard procedure. Okay, so we are now ready to compute the expectations of discrete random variables. So this is the culmination of all the things that we have been discussing so far. So let's try to describe the setting, and then we will do the computation. Alright, so let's start with this random variable x, defined on a probability space omega fp and taking values in the real line. So the measurable structure will be taken with respect to the sigma field script f on the domain side and the Borel sigma field on the range side. So suppose this is a discrete random variable, so you can now specify where the jumps are occurring. So suppose the jump points are xj, which you put in the support s, alright, and then what is the jump size? So that is nothing but the probability of x capital X equal to small xj. And another way of writing this jump size in terms of the law is nothing but p compose x inverse of this singleton set xj. So this is the size of the singleton set xj with respect to the law p compose x inverse. Alright, so this we had discussed earlier. Now recall from note 22 of week 4 that in this case the law can be written as a linear combination, a convex linear combination of the Dirac masses situated at these jump points xj, and the sum is over all points in the support, alright, and the weights that you put are exactly the jump sizes. For xj, for the point xj, you just look at the size of the singleton set xj with respect to the law p compose x inverse, and that, as we have already mentioned, this is probability of capital X equal to small xj. Alright, so this is the linear combination, the convex linear combination of the Dirac masses situated at the points in the support, and that's going to give you back the law p compose x inverse. So p compose x inverse is nothing but a convex linear combination of these Dirac masses. Alright, now remember, we have done integration with respect to the Dirac masses. We have also learned how to split the integration over linear combinations of measures. So this was discussed in propositions 4 and 5. So use that results, and what do you get? You have to now compute this kind of an integration that appeared in the expectations. Alright, so here you first use the change of variable formula to move the integration over the domain side omega to integration over the range side with respect to the measure p compose x inverse. So that's the first step. Now you rewrite the p compose x inverse, the law, as a linear combination of the Dirac masses, and as per propositions earlier, these scalars simply come out, the summations simply come out, and you only have to integrate this function, which is the identity function x here, with respect to the Dirac mass. And for Dirac masses, if you want to integrate any measurable function, all you have to do is to evaluate that function at that point where the Dirac mass is situated, and therefore integration of the identity function over this point, over this Dirac mass xj, is nothing but xj. This is just the evaluation of the identity function at the point xj, that's all. Therefore you get back your familiar series expression for expectation of discrete random variables. So this is the exact same expression that you have already seen in your basic probability course. So here what we have just done, we have started off with the measure theoretic definition of expectation of x, which was defined to be integration of the measurable function x with respect to the probability measure p, and the integration was over the domain set omega. Then we use change of variable formula to move to integration over the law p compose x inverse, and once you change this variable or measure, you end up with the integration over the real line, and you are integrating the identity function x here. But then you observe that p compose x inverse is nothing but a convex linear combination of the Dirac masses. So therefore you first bring out that summation and then bring out the appropriate corresponding scalars. These are all again non-negative scalars, positive scalars, because jumps are non-trivial jumps, and then all you have to do is to integrate this identity function with respect to the Dirac mass. So these are all the things that you are using to get back your familiar expression that you had seen in your basic probability courses. Alright, so the general measure theoretic integration that we have done already gives you your familiar expression for discrete random variables. Later on we are going to see that this general definition, while restricted to other special cases, give you back your familiar expressions. So therefore the measure theoretic integration is a general structure, and once you prove any result in this general structure, all these particular cases will follow, and you can apply all these general results to all these particular cases. So that is the power of measure theory. Alright. So with this in hand, once you know how to compute these expectations, you can now make some interesting comments. Alright. So these are listed in this exercise. So what do? You start by looking at a discrete random variable and let f be measurable. Alright. So now look at the composition of f with x. So that is nothing but f of x. So you can immediately claim that f of x is a random variable. Call it y. Now what the first thing that you need to show is that f of x, which we are now calling as y, is a discrete random variable. So that is the first statement. Now once you have a discrete random variable, you can now try to look at its law. So first thing that you do is that you can try to rewrite the law p compose y inverse in terms of the function f and the law p compose x inverse of x. Okay. So use these two quantities, the function f and the law of x, to write down the law of y. Okay. So that is the second expression. The third thing is that once you have managed to identify the law, you can also try to write down the probability mass function of y. Since y is given to be discrete, you can talk about the probability mass function. So therefore, the probability mass function of y, you can try to write it down in terms of the function f and the PMF of x. Alright, so that's good. And the interesting comment here is that you can now talk about the expectation of the random variable y. And as per our understanding, you have to do integration of the identity function with respect to the law of y, which is p compose y inverse, and the integration has to take place over the real line. But now we are saying this integration, if it exists, it will be equal to an integration over the law of x p compose x inverse, and this integration is still over the real line, but you are now supposed to integrate the measurable function f. Alright, so this is another way to compute the expectation of y, that is through the law of x. Okay, so provided one of the integrals exists, the other one will also exist. Okay, so this is again application of the change of variable formula. Try to work this out. But then using this observation, you can now justify the following for this special case that we are discussing. So here everything is discrete. So expected value of y is nothing but this linear combination over the support of y. So S subscript y denotes the support of y. But then you have this series expression which can be rewritten in terms of the summation over the support of the original random variable x. So what do you do here? You look at f of x and weight it with or factor it with these jump sizes. So if you combine these things together, you will get back the expected value of y. So this is simply another familiar expression to you that will allow you to compute expectations of functions of random variables. So all you have to do is to choose the right measurable function f and just do these computations. Okay. So again, here we are doing the summation over support of y on the left hand side here, and here we are doing the summation over the support of the original random variable x on the right hand side. Okay. And as mentioned earlier, you can choose this appropriate functions f to talk about moments of the random variable x. Okay. So you can talk about this moments of x, nth moments of x about any point c. Okay. So all you have to do is to choose this function f to be small x minus c raised to the power n, defined for any real number small x, right? So if you choose such appropriate functions, you can combine or compose with x and you can get these moments. Alright, so you can now try to compute this kind of moments for the cases when x is some known standard discrete random variable. For example, you can choose x to be a degenerate random variable or from Bernoulli, binomial or Poisson random variables. Okay, so in all of these cases, try to work out what is the expression for the moments following this measure theoretic discussion. So try to work out the values and you will expect that you will get back your familiar expressions that you have already seen in your basic probability theory. So this completes the discussion for computation of expectations for discrete random variables, and we have now seen this as an application of the measure theoretic integration. For the other type of random variables, including the absolutely continuous random variables, we have to develop this measure theoretic structure a little more, but then we would like to make similar comments about absolutely continuous random variables and their expectations and moments. This we are going to see in later lectures. We shall continue this discussion in the next week. We stop here.